Okay, hello everyone. Here's some homework help according to the requests on Canvas and discussions. The first one is for 16.1. This is for 16.1 number 15, and so I have a similar example instead of this for 16 point number 15. So we have this contour plot here, and it's showing, we know the contour lines show function values or z values, right? So these numbers, 1, 2, 3, 4, 1, 0, negative 1, 2, those are z values or the f of xy. So like right here, so f of 5 comma 5 would be 1 because the contour line for 1 goes through the point 5, 5. So that right there is showing that f of 5, 5 equals 1. That's the z value. Okay, so, and these problems, what these problems are about double integrals and estimating double integrals. And so we're estimating them with Riemann sums. So what we're doing is we're estimating values of z, right, times a dA is a little region that has a change in x and a change in y. So dA, another way to write that is like dx dy. And so the integral then is like accumulating or summing up all of these products, z times dx dy. Okay, and so we'll see in the next example how that, and you saw in the videos how that have a real world kind of application, but for now we'll just speak theoretically here. Z times dA, so we're going to have many of those and we're going to sum all those up, and so that can be approximated by, say we want the region, I'm in light blue here, I've shown the region where x goes from a -8 to -2, and y goes from 4 to 10. And we're using dx values of 2 and also dy. So each one of these intervals in these boxes, dx is 2, dy is also 2. And so these are kind of biggish dA values, right? Biggish dAs, and we have 9 of them, right? So we have 9 2 by 2 dAs, or dx is 2, dy to 2, so therefore dA is equal to 4, 2 by 2. And so to estimate the value of the double integral, we are going to assume that for each one of these dAs, you have a constant z value. Now clearly it's changing. Look, here z is 2, then z is 1, then z is 0. So across this particular dA square, the z value, or the function value, changes from 2 to 0. So it's constantly changing. But for purposes of the estimate of this, we want one z value in each of these squares. So there's kind of two ways to do this. You can eyeball a z value by looking at the lines, kind of like what one z value would kind of represent what we're seeing by the contour lines, or you can pick a corner, like systematically pick the same corner for every square and just pick off that z value for that corner. So just the eyeball method has more to do with, say, number 15, because they're asking us to say whether the overall sum, the overall double integral, is positive or negative. So for an eyeball method, we could say, oh, okay, well, this is like 2, 1, and 0, so we'll just call this one in the middle 1. Right, so we're saying the z value for that whole square is 1. What about for this? Well, 0 goes right through the middle, so we'll call it 0. And for this one, there's 0 here and -1 up here, so maybe -1/2. Okay, for this one here, again, 0 is going kind of right through the middle, so we'll say 0. Here, -1 goes right through the middle, so say -1. Here, -2 is through the middle. Say -2. Here, -2 goes like this. It might get a little bit higher than -2, but we'll just keep it at -2. All right, -1 kind of goes through the middle there, and then 0. So assuming for each one of these squares that the z is constant, and we're just kind of picking off kind of the closest kind of average for each square based on the contour lines. So then to find the estimate for this double integral across this region, which r goes from x is -8 to -2 and y -4. So in this y goes from 4 to 10. So that's this square right here. The estimate would be -2 times the dA. So these are our function values, or what I estimated from the contour lines, and then I have my dAs. They're all 4, 2 by 2, right? 2 times 2. So -2 times 4 plus -1 times 4 plus 0 times 4. So using this eyeball method, it'd be like -2 times 4. That's FDA. -1 times 4 plus 0 times 4. That's the top row. -2 times 4. -1 times 4 plus 0 times 4, and then -1/2 times 4 plus 0 times 4 plus 1 times 4. So that is clearly going to be, just looking at that, I have -2, -1, -2, -1. I have these zeros, and then only -1. The only positive value is here at 1. So clearly, this estimate, when I add all this stuff to b, is going to be less than 0 or negative. Why? Because the predominant z values or function values in this square are negative here on the upper through this whole left-hand portion of this region. And there's only this little lower right corner where the z values are positive. So the overall effect of kind of summing that all up, each one times its respective dA, the overall effect is going to be a negative total, a negative sum. So that's kind of an example for number 15. So for number 16, you're not given contour lines, but you're actually given actual points. So you can make a graph in 16 and plot those points. So for example, let's use upper right corners here. So I'll erase my, let's see. Okay, so I'm gonna start over. So that was just kind of like eyeballing best guess for the constant z value in each dA. And now I'm going to do upper right corners. So upper right means I'm going to pull off the z value. At each upper right corner, and let that z value be the assumed z for the whole thing. So here, upper right corner, 1. Here the upper right corner is a little bit greater than, so here's 0 here, and here's 1 here, so maybe 1/4. All right, here this one is 1. The upper right corner for this box goes through the z value of 1. And then upper right corner, -1 here. Upper right corner would be closest to 0, right? It's pretty close to 0 there. Upper right corner here is halfway between -2 and -1, so -3/2. And then upper right corner here is -2. And then upper right corner here is -1. And here is 0. So now, instead of just kind of eyeballing the best estimate for what z would be on an average over that, I'm particularly getting the particular z value at the upper right corner and calling that the z value, or the function value, for the whole square. So it would be the same estimate now, but rather than these ones that I picked off by eyeballing, I would be using the upper right corners. So it would be, this was -3/2, right? This is let's redo it. What did I say for this? Oh, upper right corner. Yes, upper right corner was -3/2. I just didn't write that clearly at all. So -3/2. Okay, so -3/2. That'd be -3/2 times 4, 0 times 4, 1 times 4. I'm just going across here. -2 times 4, -1 times 4, 1/4 times 4, etc. And then adding all those up. That's what this double integral means. Adding up a bunch of z times dA, z times dA, z times dA, and adding all those up. So we would get a different estimate now, right? So it still is going to be negative, probably, just looking at the numbers. But it's going to be a different sum than this first approximating method we did. So doing that is more similar to number 16, where you're going to make the graph yourself, and you're going to use those given values in the table as, say, upper right corners or lower left corners. Okay, so these limits of integration are x values. So that's, because it's x, this is really x equals y squared, and this is really x equals y. And integrating, so integrating from y squared to y, so let's sketch that. So what is x equals y squared? X equals y squared is a parabola that opens this way on the positive x-axis. And then x equals y. So this is x equals y squared, and x equals y. And then y equals 0 is here, and y equals 1 is here. So this is like the left boundary because it's an x value, and this is the right boundary, and this is like the bottom and the top. So which region has this on the left, this on the right, from 0 to 1? So on the left, this is the left side, and this is the right side. And then here y is from 0 to 1, would be this region right here. So we're talking about left and right, because dx, right? X is the horizontal coordinate, left to right. And then the lowest point, like the bottom point, to the top point is 1. So bottom is 0, top is 1. Okay, that's number 2. Let's look at number 9. So for 9, so we're evaluating now. So evaluating these double integrals is like doing, or when we did partial derivatives, so this is like partial integration, x, y. So we start here. Our starting point is with respect to x. So this is, so dx. This is our first. So we kind of isolate this right here. And we work on this as a single integral, but it's like a partial single integral, like just like our partial derivatives. So with respect to x means that y's are constants. So just like we did with the partial derivatives. So we treat y as a constant. And so what is the antiderivative of a constant times e to the x, basically? Well, the antiderivative is, so we're going to hold on to this outside 0 to 1, and the dy. So we're doing do the inside integral first. So antiderivative of e to the xy is, if you remember your derivatives, e to the xy. Okay. But when this is actually like the chain rule, right? So if you think about doing the derivative, of e to the xy with respect to x, what would you get? You would get e to the xy times the derivative of the interior function by the chain rule, which is y. Well, notice that's what we have, right? So that's exactly what we have. We're doing the antiderivative of this. So the antiderivative of this is e to the xy. I just showed that because by taking the derivative of e to the xy, I get e to the xy times y, or this. Right? So the antiderivative of y e to the xy is e to the xy. And now we're doing that with respect to y. So again, so we're doing an antiderivative. Oh, sorry, we're not done yet. We got to plug in our 0 and 1 for x, right? So we still have to evaluate at 1, evaluate at 0, and subtract. So we're not quite done with the first integral yet. So we got 0, 1. So we're going to plug 1 in for x, so e to the 1 times y, minus, plug in 0 for x, e to the 0, dy, which is e to the y minus 1. Okay, so now we've got a standard Calc 1 integral where we can do antiderivative of e to the y is e to the y. Antiderivative of minus 1 with respect to y is minus y. And we're going to evaluate from 0 to 1. And now we're home free. E to the 1 minus 1 minus e to the 0 minus 0, which equals e minus 1 minus another 1, minus 2. Okay, so these double integrals, the way that you evaluate them is very similar to when we did partial derivatives. It's like partial integration, where when you take the integral with respect to x, your y's are like constants. So you treat them as constants. And so we showed that e to the xy is the antiderivative of that. By taking the derivative of e to the xy, we got exactly this derivative. So its antiderivative is e to the xy. Plugged in our 1 and 0 and subtracted. And then we have a standard Calc 1 single integral. Okay, hope that helps. Move on here. So that was 15. Okay, so now our first integral is with respect to y. So again, we're isolating this inside integral, evaluating that first. And with respect to y, so this is, doing this antiderivative would be like doing the antiderivative of, like, say, e to the 6 plus y, right? X is considered a constant. So what function gives a derivative of e to the 6 plus y, right? Think of this as a derivative. What function, if we took the derivative of it, would give us, say, this? Well, I think it's just e to the x plus y, isn't it? So what is the, so let's conjecture that. E to the x plus y, what's the derivative of e to the x plus y? Well, it's going to be, derivative is e to the x plus y times the derivative of that with respect to y, which is just 1. So it is. So this is its own derivative with respect to y. E to the x plus y, there's an antiderivative. So we know derivative and antiderivative of an exponential function is itself, right? So I just wrote down itself, thinking, okay, the antiderivative is e to the x plus y. But to check it, I'm taking the derivative of that to see if I get exactly what I started with. If I do, then I confirm that this is the right antiderivative. And that's what I did. I took e to the x plus y. The derivative is e to the x plus y times the derivative of the interior with respect to y, which is 1. Therefore, I got what I started with. And that's my check that this is the right antiderivative. Okay, so it's going to be 1 to 3 of the antiderivative of e to the x plus y, and that evaluated from 0 to 4. With respect to y, right? So we're going to plug 4 in for y, 0 in for y. I'm going to get e to the x plus 4 minus e to the x. And that from 1 to 3. And I'm going to stop there and let you finish it on out, because now you got a standard Calc 1 integral. Antiderivative of that, antiderivative of that. Subtract, and then plug in your 3 to the antiderivative, plug in your 1 to the antiderivative, subtract, etc. So you finish that one. Okay, hope that was helpful. You've got homework is due at 1:40 p.m. Quiz is at 2 on Tuesday. And then we're going to meet in my Zoom room, which is posted on Canvas, 2:20 to go over exam 2 and talk about the retake. And that's mandatory. Everyone's showing up for virtual class to go over exam 2 and talk about the retake exam. Okay, we will see you tomorrow.